Okay, welcome everybody. In today's lecture, we are going to look at how to find the absolute maximum and absolute minimum of a function on a closed bounded set. So you've seen a couple of examples, and I want to do another one where the only thing that you're given is the function that you want to maximize and minimize. And then you're told you maximize and minimize that function on a region, which is a quadrilateral, and then they give you the endpoints. Okay, so here I've plotted the endpoints. We see it's a quadrilateral. So the region I want to maximize the function on is the shaded part plus the boundary. So that's a closed bounded set. Okay. So how do we maximize a function on a closed bounded set? Well, we know that the maximum has to occur either at a critical point in the interior or on the boundary itself. So we're going to have to characterize the boundary of this region, and that consists, in this case, of 4 separate lines. So it's the line, let me call this one L1, let's call this one L2, this little line right there, L3, and this long slanted line L4. So we're going to have to consider maximizing the function f on all 4 of those lines, plus find all the critical points that are in the interior. And then check the value of the function at all those points. And then the largest one is the maximum, and the smallest value at all those points is the minimum. So in principle, it's pretty easy. In practice, these problems tend to be quite long. So expect them to be long, and you have to be careful not to get lost in the process as you're doing it. Okay, so we want to start, the first thing we're going to do is find the interior critical points. Okay, so to do that, we take f sub x and f sub y and set them both equal to 0. So f sub x is going to be 3x squared minus 3. And when I set that equal to 0, I get x squared equals 1, which tells me that x is equal to plus or minus 1. And don't get sloppy with your algebra and lose half of your critical points. And f sub y is minus 3y squared plus 12. So when I set that equal to 0, that tells me that y squared is equal to 4. So that y is equal to plus or minus 2. Again, you must be careful with your algebra. So that means I get 4 points out of this. I get 1, 2, 1 minus 2, minus 1, 2, and minus 1, minus 2. But now when I look up here at my region, 1, 2 is about in here somewhere, so that's okay. But when I look at 1 minus 2, that would be down here, which is outside of R. So I don't use that one because it's outside R. And likewise, minus 1, 2 is fine, it's up here somewhere. But minus 1, minus 2 is down here outside the region. So it is also outside of R. So from this, we get the points. We'll make ourselves a little list over here, places that we have to check. So let's do the points and then the value of f of x, y. So we have 1, 2 and minus 1, 2. Okay. And if you check, so now I just take these values 1 and 2 and I plug into the function and I'll work out what I get. If you do that, you will see that you get 14 for f of 1, 2 and f of minus 1, 2. So I just plug into this. That gives me minus 1, and then I get a plus 4, and then I get a minus 8 and a plus 24. And when you add that all up, you get 18. Now we're going to have more to add to this list as we go along, okay? All right, so we'll just keep that list over there, and we'll keep coming back to that list as we add more things to it. All right, so now we want to start looking at what happens on the boundary. So let's look at what happens on L1. On L1, we notice that L1 is the line, and now it's just the line. I don't think you have to work this out. I think everybody can figure out that this is the line x is equal to -2. Okay, so on the line x equal to -2, what does the function look like? It's f of -2 comma y. So let's see, that becomes -8 plus 6 minus y cubed plus 12y. So that gives me minus y cubed plus 12y minus 2 is my function. And you see that's a function of y only. If you like, you can rename this. So it reminds you more of calculus 1. Let's call it, I don't know, g of y is as good as anything. So now you want to maximize and minimize g. On this line L1. That's a calculus 1 problem. How do you do that? And why do I say it's a calculus 1 problem? Because on L1, remember the only possible places you can go, L1, on L1, y takes the value from -2 to +3. And that's it. That's the only piece of that line segment we have. We don't have every possible value of y on the line x equals 2 for L1. It's just that line segment. So now when we take the derivative, by calculus 1, you take the derivative and set it equal to 0, and you look for critical points or the endpoints. So you maximize and minimize g on L1. So this means y is between 3 and -2. Okay. All right, and so the maximum of that function either occurs at a critical point of g, which is -3y squared plus 12, equal to 0, which says y squared equals to 4, which says that y is equal to plus or minus 2, or it happens at an endpoint. So that means that the possible critical points that we have to add to our list are -2, -2, -2 plus 2, and -2, 3, because that's an endpoint of this interval. Okay, that's where another endpoint for y, and by calculus 1, the maximum can occur at the endpoints. Okay, so that's it on on L1. Now, what about on L2? On the line L2, let me put it so we can see the line L2. Okay, when you look at this, you can see the line L2. That is the line y equals 3. And that's when x goes between -2 and +2. Okay, so now we write out the function with y equal to 3. So f of x comma 3 is x cubed minus 3x minus 27 plus 36. So that is x cubed minus 3x plus 9. And that's a function of y only. So let's give it a name that reminds us more of calculus 1. How about h of y? Okay. And now h of x. Blah. It's a function of x. Okay. And so now how do I maximize this by calculus 1 on this interval? You take the derivative, set it equal to 0 to find possible critical points if you have any. So that is 3x squared minus 3. And now you set that equal to 0. That will tell you that x squared is equal to 1. So x is equal to plus or minus 1. Okay. So x is equal to plus or minus 1, and y is equal to 3 are critical points, plus those endpoints. So that from this interval, we get the points 1, 3, minus 1, 3, minus 2, 3, and plus 2, 3. Okay, so we go back to our list, and now we have some other points to add. But notice some of those points are already listed here. The point we said we just had it, we have to add the points 1, 3, minus 1, 3. So we need 1, 3, minus 1, 3. And we said minus 2, 3, and 2, comma 3. Well, minus 2, 3 is already there. Now we have to add 2, comma 3. Okay. Okay. That list is getting long, but that's just a plug in and check. So that's not too bad. All right. Now we go on to line 3. On L3, well, we notice that L3 is the line x equals 2. Okay, so now when x equals 2, we look at the value of what is the function. So that's 2, comma y. And if we look back at our function, well, I can't fit it all in now. Well, here I can this way. So when, oops, sorry, just dropped my pen. Hope I didn't break my fountain pen. Okay, we shall see. So now when x is equal to 2, we get 8 minus 6. And then we have minus y cubed plus 12y. And so this becomes minus y cubed plus 12y plus 2. And notice that's a function of y only. So we can give it a name that reminds us of calculus 1. So I don't know, we had a g before of y. Let's call it g tilde of y. And now we have to maximize g tilde, find all the maximum when, whoops, we forgot to write down that in our graph on L3, y only goes between 2 and 3. So this is y between 2 and 3. Okay, so we need to maximize and find the maximum and the minimum of g prime of y. The possible places that could happen are at critical points or at the end points. Okay, so let's see. Let's find the critical points. So g tilde prime of y is minus 3y squared plus 12 plus 0. We've seen this a couple of times before. That gives me the y is equal to plus or minus 2. Since y squared is 4, so that's y is plus or minus 2. And so my points that I get from this one are 2 minus 2, 2 plus 2, and the endpoints. But the endpoints were 2, 3, and 2, 2. And 2, 2 we got before. So let's go back to our list and add in those points. So 2 minus 2, 2, 2, and 2, 3. But 2, 3 was already here. Okay. So of the 3 new points, we only had to put on that list 2 extras. And now finally, we're ready for the last line. Okay, the last line, notice L4 is the line that goes through minus 2, and plus 2, plus 2. Okay. So on L4, so L4 is the line through minus 2, and plus 2, plus 2. Okay. So now it's not one we can just eyeball and say we actually have to find the equation of that line. So how do you do that? You find the slope. So that's the difference in the y values. So that'll be 2 minus minus 2 divided by the difference in the x values, x minus minus 2, 2 minus minus 2. So that is 4 over 4, so that's 1. So that's slope 1. And it goes through the point 2, 2. So that'll be y minus 2 is equal to 1 times x minus 2, which says that x is equal to y. So that means my picture was really bad. My picture looks like it misses the origin, but that's just because I drew a bad graph. I didn't have everything equally spaced. So that's okay. As long as we check with our algebra, the picture doesn't have to be perfect. Okay. So x is equal to y. Okay, and so that means when we look at our function on L4, it can look like either XX or YY, whatever your favorite version of the function is. And so let's see, that means our function is going to be, if you look back at F, that's going to be x cubed minus 3x minus x cubed plus 12x. Okay, and so the x cubes cancel, and we get that f is just 9x, and that's as x goes between minus 2 and plus 2. Okay, so now we take, that's a function of x only. Let's call it h tilde of x. Okay, so we take the derivative. That will be 9. So it's never equal to 0. So the only critical points you get are the two endpoints. So the only 2 points you get from here are minus 2, and plus 2, plus 2. So we go back to our list and we make sure if those are not there already, you put them in, but they are. Okay. And now we have to go back and check the value of the function at each one of these points. Okay, so now it's just a pretty easy matter to go back and plug these values into the function. And when you do, you will get the value at minus 2, minus 2. You see, it's easy to do that when you look at that. You have on L4, when x and y are equal, the function is just 9 times, if x and y are equal, pick your favorite one, then it's 9 times the value, so that's minus 18. Okay, so you can plug in different ways. You will get minus 18, 14 for this one, 7 here, 7 there. You can go back and check these. It's just routine arithmetic, 11. And then you get minus 14 and 18. Okay, and so that's the list of the value of the function, either at a critical point in the interior or on the boundary at a critical point or at a boundary point. Okay, and so now we look at that and we look at our list. The largest one's the maximum. So the maximum is 18, and it occurs at 2 places. So the max of the function is 18, and it occurs at minus 1, 2, and at 2, 2. And the smallest value you see is minus 18. The min is minus 18, and that occurs only at the point minus 2, minus 2. Okay. All right. So minus 1, 2, notice is a point minus 1, comma 2 is a point that's on the line when y is equal to 2. Sorry, minus 1, comma 2 is an interior. Sorry, the wires are in the way. The minus 1, comma 2 is an interior critical point. And that, so the minimum, one of the places where the maximum occurs is there. The other is at 2, 2, which is a corner of the region. Okay, so the other place where the maximum occurs is right there. And the minimum occurs at minus 2, which is another corner of the region. Okay. All right, and so all of that goes into this one, solving this one problem. So these problems are quite long and they take a while, but they are important because you, when you apply these ideas to real world applications, you are often maximizing and minimizing things on some closed bounded set given by some constraints that the problems give. Okay, so that's it for today. Hope that helps. Now try your homework problems for this section.